Hey, welcome everyone to topic 11. This is going to be called Remote Sensing for Habitat Quantification. I will be the lead, Tyler, and the historian will be Colin. And this should be a pretty cool paper, and I'm excited to get started. Thank you. Okay, so here's our main paper, guys and gals. It is the production of global daily seamless data cubes and quantification of global land cover change from 1985 to 2020 using IMAP World 1.0. Here's a list of our authors. So let's go ahead and get started. So just a little overview here from the paper as it begins. The ability to achieve high resolution and high frequency, high observational data can be difficult to achieve based on the current technological constraints. So what this team did was made an entirely new paradigm for mapping. And this is in such to fill the gaps that they believe are missing. So they created an automated, seamless end-to-end production chain and parallel mapping system. Uh, the results of the experiment were to produce the first ever 30-meter daily seamless data cubes, and they used a litany of remote sensing tools and deep learning AI. The SDC was produced through a multi-source, multi-temporal data reconstruction fusion workflow based on Landsat, Modis, and AVAR virtual constellations. They then independently validated their results. Their average accuracy over the annual land cover maps turned out to be roughly 80% for level 1 classification and 73% for level 2, although they had a lot of other classes that they classified their accuracies in, and not all of them were that high. So there was some, alternate estimations there. Here's a slide for just showing you a list of the remote sensing tools that were used to make the seamless data cubes. And this is by no means a complete list. This is the majority of stuff that they mentioned throughout the paper, but there's quite a few other, what I believe are just computer programs that they use to view images and different data that they overlay it with. Not all of these are remote sensing tools. Most of them are. A lot of them are also just that, some computer programming tools. So this is a figure from the methods section of the paper, which encompasses about 15 pages. Overall, the framework for the seamless data cube is illustrated here. This is sort of the evolution of mapping cognition in humans using intelligent mapping, or IMAP. It's introducing the IMAP framework, and it leverages advanced technologies such as artificial intelligence and cloud computing to address challenges in remote sensing. It includes data processing and reconstruction, fusion to generate seamless data cubes. It will cover spatial temporal fusion for enhanced accuracy, and post-processing ensures high quality land cover maps with the entire process implemented in cloud computing platforms like AWS. So in this slide, the bar chart here is representing the Thermatic Mapper, the Enhanced Thermatic Mapper Plus, and the Operational Land Imager. And there's a little code there at the top so you can tell which ones are which. And this is ranging from the years 1985 to 2020. And for this figure, they used a strategy to fuse the available reconstructed Landsat imageries with AVAR to fit Hermetic models. They would then input the Hermetic predicted Landsat images and reconstructed AVAR images on the same day into spatial temporal recursive guided fusion to obtain the daily Landsat data cube. for 2000, they used the Landsat images obtained by fusion models with MODIS into harmonic model fitting, and they used predictions from deep learning fusion models and introduced those to perform their harmonic modeling fitting of the previous years as well. And they took random samples from around the world and fake harmonic predicted Landsat high resolution imagery and true guided AVAR low resolution imagery on the same day and put them all together to kind of drive this deep learning model that we're starting to get a view of. So this is the seamless data cube, feature cube construction, and this table over here breaks down how they put this together over 1985 to 2020. This data cube is going to encompass a lot of the indexes that we've used in our class, like the normalized difference vegetation index. I haven't seen the normalized difference water index, but there's that, and a normalized difference built up index, a normalized burn ratio, and all of these bands were, all of these indexes were calculated to reflect phenological information from different band lengths over, the 30-year period. And then through that, they used some other like co-occurrence matrix and gray level co-occurrence matrix, and extended multi-attribute profiles. So there's a lot more to the validation process than this slide is going to encompass, but I left a table in here for you, and I left the class code as well. So on the top left of the table and all the way down, you'll see 10, 20, 30, 40, 50. These are all codes represented at the bottom of that figure. And off to the right is the percentiles of accuracy. And they selected 500 random tiles for testing. The validation samples were randomly sampled from globally equal area hexagons. Confidence in classification results was recorded to reflect classification performance and quality over space. They used random forest samplings, extreme randomized trees, K nearest neighbors, boosted trees, cap boosted trees, and neutral networks. And these were all assembled and stacked together to create a more streamlined workflow of the SDC and increase accuracy. And this is just a picture of Part A and Part B of their training samples versus the validation samples taken in 2015 using FluxNet samples. The different colors represent different from GLC level 1 classes. The detailed distribution of the samples amongst the classes are shown in that pie chart on both the slides. Getting into the global mapping results here, this is what the authors have done all their work for. So we're finally getting into the meat and potatoes of this paper. Both these maps look similar at first sight, and there's some color codes there at the bottom that you can match the colors up with. But they're both using from GLC and LCC classification systems. There was a couple differences in these maps. The most significant difference amongst these two are going to be the seasonal variations in snow and ice that you can see in the Northern Americas there. There's also some other differences amongst croplands in central U.S. and northern China, if you could spot those. All right, so here are our findings for the paper. After all that work, we have trend of land cover change from 1985 to 2020. There's quite a bit of information on the slide here, but in general, I'm just going to hit some of the bigger ones. Forest, that was the class with the largest rate of change, and it decreased by a total of 1.47 million kilometers squared. The largest decrease of 6.6% was observed in South American forests, while the lowest decrease of about 0.08% was observed in Asian forests. down here towards the bottom, we actually had global wetlands and water body increase of 80,000 and 380,000 kilometers squared. Oceania was the only continent where the area of water body did not increase. Global change in croplands was second only to forests with an increase of 840,000 kilometers squared. Among these, croplands in South America and Africa increased by 530 and 260,000 kilometers squared, accounting for 63.1% and 31% of global increase in croplands. So the rest you can read, and we'll move on to the next one. Here's a global land cover map for 4 seasons. Pretty clear to tell the differences between these 4 images, and you can certainly see where winter picks up and spring and fall begin. Very well. Let you look at that for a second. Here's another type of a map for global land cover changes. This one spans the 35 years here, and this was probably my favorite map of the paper. I think it's, if you all can see the bar chart over here on the right, it definitely depicts forests on nearly every continent on the downtrend, whereas croplands, grasslands, and shrublands are on an uptrend, most specifically croplands. So forest down, crops up. So here we have another chart. This is global land cover change rates and conversions. So this one's kind of cool. The pie charts in the middle are showing you, how much percentage-wise the color code is, and at the bottom you can find the right color for what piece of the pie you're looking at. As far as the kind of stock candlestick chart up here, didn't really understand it, but the way I'm sort of looking at it, if we're looking in the polar region, there's very little to no activity, and it's definitely lower than everything else, and the most active activity is going to be in the tropical and subtropical regions, or the temperate regions. I guess even the boreal region. But anyway, so these conversion rates are kind of grasslands to croplands, forest to grasslands, shrublands to grasslands, cropland to forest, barren land to cropland, barren land to shrubland. So have fun looking at that. Okay, here's another image that I felt like should be included in this PowerPoint. This is like the Google Earth versus the author's proprietary imagery, I guess. So at the top two linear lines from left to right, we have a Google Earth image, and then we have the author's image. And that is representing the urban expansion in China. And it really matches up, if you can see that on the PowerPoint, or I guess you can look at it in the paper when you open it, but definitely matches up really close. And then at the lower, we have croplands that are expanding in Brazil. So again, Google Earth is right above it, and the lower image is the author's image. I thought it was a worthy slide. All right, we're finally getting done. The conclusions. Authors have adequately fused remote sensing data, revealing advancements in global land cover mapping from 1985 to 2020. The mapping identified seasonal and annual dynamics involving 2 classifications and 30 subclasses, which significantly enhances the efforts here. They utilize Landsat, MODIS, and Aadhaar data. The research team developed the first ever set of global daily seamless data cubes. And the global average land cover change rate is 0.36% per year, with notable increases in croplands and drastic decreases in forests. And this work implications are suitable for global environmental change research and land resource management. So I wanted to have two different types of questions here. The first three questions are going to regard the paper, and the last two questions are going to be opinion based. So feel free to pick one from each and have fun with the discussion board. And if you want to write about something entirely different, this is a very vast paper and there's lots of different nuances to explore in the paper. Please feel free to start a discussion off with whatever you want to talk about in the paper as well. Thank you for your attention and have a great day.